welcome you all to this class on diffraction and imaging. In the last class, we considered symmetry elements associated with two-dimensional lattice, both the point group symmetry and the two-dimensional space group symmetry we discussed. On the same line, today we will discuss the three-dimensional point groups and space group symmetry. Okay, I have told you earlier itself that what is the need for having information about the point group symmetry, because the properties of the material essentially exhibit point group symmetry, including when crystals form their external crystal form. One can look at it and identify the symmetry elements which are associated with it. Okay. What are the symmetry elements which we considered for point group in two-dimensional crystal? Symmetry elements which we considered: rotation, then rotation, mirror. Okay, these are all the two symmetry elements which we consider. Okay. In the case of a three-dimensional lattice, we have to consider, in addition to rotation and mirror, we will be considering inversion also. But I had already mentioned about what an inversion is. Okay. So, rotation, reflection or a mirror, inversion, and we can generate symmetry elements taking combination of these. Okay. Then we can have what is called as a roto inversion. Okay. That is that in the last class on Saturday I explained to you, okay, how this what roto inversion means and how it is done. Okay. So, if we take the combination of all these, okay, we will be getting different type of symmetry elements which we will be generating. Okay. This will constitute some distinct number of symmetry elements, okay, that in general turns out to be 32 point groups. Looking at the type of symmetry elements, one can talk about what is the sort of property which the crystal will exhibit. How to construct the stereogram, okay, and for different point group symmetry elements, that we have done as an exercise in the last class. Okay. So, that is what essentially I had shown it here. This is an one-fold symmetry, okay. Then a two-fold symmetry, that point which we take, that is rotated once 180 degree and then again rotated. This is the symbol which corresponds to two-fold symmetry. Like this, we can have three-fold, four-fold, six-fold. So far, we have considered the various symmetry operations like rotation, mirror, inversion, screw and glide. All these operations can be represented, okay, in mathematical terms to find out the coordinates of the different motifs after these various operations by what is called as a Sitz operator. What is that? Sitz operator is represented in this way, that is r stroke t, that is operating on small r. This small r represents nothing but the position of the motif or the lattice point, and r represents essentially the type of symmetry operation. T represents the translation which is associated with the symmetry operation. This itself can be written as r into r, where this plus t, where t is not equal to 0. Okay. These are essentially what we mean by rotation or symmetry or rotation or mirror or translation. Okay. Suppose we consider a identity operation, okay, that is 360 degree rotation around a point. Then this r will become 1, that is 1 stroke, and there is no translation associated with it, then it becomes 0. Then this is called as an identity operation, which brings the point after the symmetry operation back to its original position. Suppose it is only a translation which is involved, but that is only a translational symmetry is operating, no other symmetry, no other rotation or mirror or inversion symmetry. In such a case, we can put it up this way, that this 1 represents the identity and Tn represents the translation, then Tn could be T1 into A plus T2 into B plus T3 into C, where A, B, C represents the lattice translation vectors. Suppose it is mirror, and the mirror is on 1 0 0 plane, then this is the way this could be represented. Okay. Similarly, if it is a glide which is along that axis is going to be there, okay, then what it will essentially represent is that here we will be putting the rotation symmetry, okay, plus what is going to be the pitch corresponding to a glide, that will come as the T. That is the way we can represent this. So, in short, using this operator, okay, and the matrix transformation matrix associated with the different symmetry elements like rotation, inversion and mirror, okay, we can find out the coordinates of the other points after the symmetry operation. What we have considered there are just pure rotation, okay, and rotation and inversion, how it is represented in a stereogram, the point group symmetry. Okay. I mentioned also earlier that rotation itself, we can consider a combination of it. If we take a 3-dimensional crystal, okay, we find that in one particular direction, okay, there is a symmetry element which is associated with it. Okay, a two-fold rotation is there. And if we look into other directions which are non-coplanar with it, we will see that there may be some symmetry elements which are associated with it. Okay. What are the types of symmetry elements which are possible in other directions also? That is what essentially is given in this table. Here what is being shown is what are the symmetry axes which are being considered. A crystal which we have considered, we find that there is a two-fold rotation is there. Okay. Then another two-fold rotation is there along B and another along C, and all these axes are 90 degree with respect to each other. Okay. So, two-fold and 180 degree, and the only lattice which can have this sort of symmetry element is essentially an orthorhombic crystal, right. Suppose a lattice has got a two-fold and a three-fold, okay, then that is essentially a trigonal lattice. Okay. Similarly, if a lattice has got a two-fold and a six-fold, okay, that lattice will essentially be a hexagonal, right. Right. Suppose a lattice has got a two-fold and a four-fold, what it will be? It is a tetragonal. Okay. If a lattice has got two-fold, three-fold and a four-fold, then that lattice will be a cubic type of a lattice, right. So, this is the sort of combinations which we can have. Okay. Similarly, we can have a here we have considered only pure rotation. The combination could be of pure rotation, okay, and a roto inversion also. Similarly, we can have combinations, okay. That also can be considered, that will give rise to some symmetry elements. If we consider all these symmetry elements together, the distinct number of symmetry elements which we can have is essentially 32 point groups which we can have. Okay. All the point group stereographic projection of the 32 point groups are given in this as well as the next transparency. Okay. Are you able to see it? Here it is for a cubic. So, essentially what one can make out is that these are all the various symmetry. What do we mean by 32 point groups? That is, suppose we take a crystal growth itself, okay. That different type of crystals which can form, they can exhibit external shapes corresponding to this sort of point group symmetry, correct. Or if you look at the property of a material, if you are looking at a dielectric property of a material or a magnetic property or elastic constants of the material, okay. What are the types of symmetry which the property can exhibit if we measure the property on a single crystal, okay. and then if you try to group it into different directions when they form, find out what all the directions in which they are there, and we will invariably find that all these axes, okay, intersect through a point, okay. In some cases it will be only a plane, some cases it will be only an axis which will be there, which is invariant. Then we say that these are all essentially a point group symmetry, because at least one point is left invariant in that symmetry operation. Is this clear? But what you can do it is that these slides I will anyway send it to you. You go through it. I had given us some assignment also to you people to generate. Okay, when you do that, then you will be able to understand how these stereographic projection of point group symmetries are generated. It will be quite simple. Okay. So essentially, how many symmetry elements? That is rotation. If you consider there are 5, mirror 6, right? Then roto inversion. These are all the symmetry elements. Then a combination of roto inversion and rotation axis. Okay. All of them put together, if we see, the total number as I mentioned is 32. Okay. What I will just describe briefly is, okay, so far we looked at only just the stereographic projection of it. Okay. Now what we will try to look at it is, what does it mean? Okay. Generally in a stereographic projection, what we are trying to take is a general point, okay, pole, and how the pole, okay, is repeated if the crystal has got a particular point group symmetry. I mentioned that a crystal can have, okay, special points also. Okay. So here what we are trying to do it is that whenever we try to look at a as an example, okay, the point group symmetry of a, we are trying to identify the point group symmetry of a crystal looking at its external form. Okay. For example, suppose you look at this cube. What are the external forms this has, which you can see? Only faces which are 100 type of a face, correct? That is the only way in which it is existing. Suppose you assume that these are all the axes, then what this face will correspond to? 110 type of a face also it can have, crystal can have, correct? And what are symmetry elements which are going to be associated with this one, this cube? If you look at it, a fourfold axis along all the 3 coordinates which are chosen, then twofold axis, okay, is going to be there on 110 direction, then mirror is going to be there on these axes, correct? So that is what essentially is being shown in this particular, that is what is being shown is that if a point has got a 4 mm symmetry, okay, the face it can have is only 001 type of a face. Okay. That is around this axis. If you take it, what are the faces which come? Only 100 type of a face which it comes, correct? So in this one 110 face, when they come, okay, they can have a mirror symmetry associated with it around this, as well as this a mirror symmetry is associated with it, correct? 110, and this faces also is related by a mirror. Okay, if I take a mirror axis, the mirror plane like this, okay, or a mirror plane like this, both the sides we have 100 and maybe here 010. So this type of plane also is there with which it can form. Okay, so 2 types of mirror planes can be there. Okay, it can have an external shape which exhibit mirror plane. One is with 110 face of the external form or with 100 type. Okay, that is what essentially is shown here. Okay. Other than that, it can take any other form. Like suppose I take a 1 1 1 as the face, then how many it can have? 1 1 1 face. So 8 faces will be there, correct? Okay. So this general one which corresponds to those type of symmetries, okay, HKL, which is, or it can be 1 2 3, also a face which it can form. So these are all the faces with which also the crystal can form. Okay. So essentially what is being shown here is that like this table A, B, C, essentially like the Wyckoff positions which I mentioned. Okay. This is at different points at this particular point, because the different symmetry elements passes through a particular point, right. That is the center of the, that is what we chose as the center of the origin of the coordinate system. Okay. With respect to that, 4 symmetry is essentially exhibited by, okay, axis which is passes through it because a 4-fold rotation is there, and mirror is also there, correct, this axis. Okay. And the face which is normal to it is to this pole is essentially 0 0 1, correct. Then we have these 4 faces are there, 1 0 0 type of 1 0 0 and 0 1 0, which have essentially a mirror planes which are associated with it. Then with respect to 1 1 0, a mirror plane is associated with it. Then if the crystal has got 1 2 3 type of a, then also, okay, then it will have 8 for this point group symmetry 4 Okay. In this table what has been done is that all the point groups symmetry element, the 32 crystallographic point groups are represented, okay, in a tabular form. Okay. A triclinic, because the earlier class I mentioned that these crystal classes or the crystal systems, they are determined on the basis of minimum symmetry the crystal of a particular class exhibits, correct. On that basis, if you look at it, triclinic has got 1-fold okay, symmetry or 1 bar, okay, inversion. Then if you look at monoclinic, the minimum symmetry element which is there is only 1 2-fold rotation, correct. And orthorhombic is 3 2-fold rotation. Tetragonal should have minimum 1 4-fold axis, correct. If that is there, it is tetragonal. Trigonal exhibits minimum 1 3-fold axis, okay. Hexagonal exhibits 1 6-fold axis, correct. And cubic represents, okay, a 2-fold, okay, and a 3-fold axis, 4 3-fold axis which are intersecting, okay. These are the minimum symmetry which a cubic crystal should have, okay. This side what is being exhibited is, what is being shown is the maximum symmetry element in this class a crystal which can have, okay. That is essentially if we construct a lattice, okay, because as I mentioned earlier, that is when you put a motif, okay, around a lattice point, okay, depending upon the type of motif and how they are placed, okay, the symmetry of the crystal can be equal to that of the lattice or it can be smaller than that. So in each of this class which we consider, the lattice exhibits the maximum symmetry elements, right. The different classes are defined with respect to minimum symmetry elements which are required. Maximum symmetry element which a triclinic can have is 1 bar, okay. Monoclinic can have is 2 by m. Orthorhombic can have a symmetry which is m. Okay, this will come to later. I will show some examples of the crystal structures. Then tetragonal is 4 by m. Trigonal, it is 3 bar m, okay, and 6 by mm is what the symmetry for hexagonal, cubic is m3 bar m it is written. In between, okay, there are different types of groups of symmetry elements which are possible, but what you should notice is that everywhere here twofold and the mirror, always that 2 is going to be the minimum symmetry element always has to be exhibited by all the crystals, plus some additional symmetry elements are there, but the lattice exhibits the maximum symmetry elements. Okay. So, this total together turns out to be 32. If you look at this table, the some of the like 6 by mm which is written, many of the symbols are shorthand symbols, okay, that actually the symmetry elements are 6 by m, 2 by m, 2 by m is the detailed symmetry which is there, because in the crystallography table quite often the to bring, no, you cannot say that to bring clarity, but to bring some uniformity, okay, some shorthand notations are followed, like it is written m3 bar m for cubic one. This actually means 4 by m, 3 bar, 2 by m is the symmetry elements which are associated with it. Okay. Now, I will explain what these symbols, each one of these means, because we are using always 3 symbols to represent it, correct? Is it clear? Okay. The convention which is followed essentially is that the rotation axis is the maximum rotation that is taken along the, generally along the z axis, okay, or in the stereographic projection the center of the stereogram, okay, represents that point through which that symmetry axis passes through, okay, either a 4-fold or 2-fold, like if you put it, this is the point through which the 2-fold axis is there, or it could be that here we have a, so this is a 4-fold axis, right. This is how the various axes are, okay, are represented. For a monoclinic, we have only that here if you notice it is mentioned as 0, 1, 0, okay. That is the convention which is being followed, okay. That is the 2-fold axis, the 2-fold rotation axis is along 0, 1, 0 direction, okay. And if you take orthorhombic, it is essentially the primary, all the 3 symbols 2, 2, 2, they represent, okay, symmetry elements along all the 3 axes, okay. Then tetragonal, if we see it, okay, the first letter which is 4, okay, the 4, 2, 2 if you take it, or 4, 2 m if you take it, okay, the 4 represents the symmetry element along 0, 0, 1 direction, okay, and the next one represents symmetry along element along 1, 0, 0 or 0, 1, 0, and the third letter represents symmetry elements along 1, 1, 0 direction, okay. This is the convention with which all these symmetry elements are represented in that table, okay. Hexagonal, similarly the 6-fold axis will be along 0, 0, 1, that is C axis, and along 1, 0, 0 or 0, 1, 0 it represents the next number which represents, and the third one represents either 1, 2, 0 or 1, 1, 0 type. Whereas in the case of cubic system, okay, the first letter represents the symmetry element along any one of these 0, 0, 1 direction. The next letter represents the symmetry element along 1, 1, 1 direction, okay, the third letter represents symmetry element along 110 direction. Okay. This is the convention which is being followed to represent the point group symmetry, or similarly the same convention is followed for space group symmetry also when we wanted to represent for all the crystal systems. Okay. And if you notice, trigonal has got, okay, a threefold rotation axis, correct, and cube also has got a threefold rotation axis. Okay. How they are differentiated is, okay, if I write as 3 2, okay, if the first letter is 3, that represents a trigonal. Okay. If the second letter is 3, okay, like 4 3 2 or 2 3, okay, then this represents a cubic system. Okay. This is the convention which is followed to differentiate between cubic system and a trigonal system. Okay. Is it clear? Okay. On this basis, okay, on the basis of the symmetry elements, we have got the 7 crystal systems, and then the space group lattice, how we decide is on the basis of whether it is a primitive lattice or whether it is body centered, face centered, okay, or one face centered. On that basis we have the various classification. So, we can have 14 Bravais lattices are possible. Okay. Right. In this transparency, I had just mentioned the space group symbol which is used to represent these 14 Bravais lattices. Like here it is a triclinic. Here if you see, these are all cubic one. We can have a cubic crystal, okay, with a primitive lattice. Okay. The symmetry which it exhibits is this symmetry, that is equal. So, if I put a symbol P in front of it, this represents a simple cubic lattice. Okay. If I represent I in front of it, it becomes body centered, and if we put F, then it becomes a face centered. But the point group symmetry which this crystal exhibits, or this lattice, cubic lattice exhibits, whether it is primitive or simple cubic, is essentially the same. Is it clear? All these symmetry elements will be there. These symmetry elements are only a few symmetry elements which are used to represent the symmetry, correct? But the number of symmetry elements which, if you consider, which this crystal will have, is quite a lot. Okay. That we have not looked at it. That is, 4 itself, 3 4-fold axes are going to be there, correct? Similarly, 3-fold, how many are going to be there? 8, right? No, 4. Similarly, 110, that is 2-fold rotation. If you take it, there are going to be 6, like that, okay, along different directions which are quite distinct. Okay. So, there are many symmetry elements are there. This we will talk about what are the number of symmetry elements which it can have. In fact, that is also is represented by the number of poles which you see in a stereographic projection. Generally, for a suppose this is what the stereographic projection shows. There are 8 poles which we are seeing, right? The total number of symmetry elements which it can have, this crystal, is going to be 8. Okay. There are many ways in which it can be derived, but you can take it, because just looking at the number of poles which are there, you get the information about all the symmetry operations which are possible. Okay, the total number of symmetry elements operations which are possible. Is it clear? Okay. Then we considered the various types of that twofold rotation, that is rotation, inversion, mirror, roto inversion, okay, and combination of rotation and combination of rotation and roto inversion we considered it. This number we can take different combinations. If we take various combinations, okay, the number of systems which we can consider point group symmetry are quite a lot, because that combination which one can try it. But many of them will turn out to be identical to one another, which I think in the last class when you have worked out, you could make out how it happens. Because of that only, we find that only 32 distinct point group symmetry elements are present. Okay. So far we considered only the point group symmetry. Okay. But in a crystal, in addition to point group symmetry, okay, because the lattice point gets repeated, okay, if we put a motif, motif also can get repeat itself depending upon where the motif is being kept. In some cases it can exhibit another two types of symmetry elements. They are one is glide and another is a screw axis. Okay. So for a crystal, if we consider, apart from these point group symmetry elements, these symmetry elements also come into the play. So if we take a combination of all these symmetry elements, okay, the total number of distinct groups of symmetry elements which we can have turns out to be 230 distinct point group symmetry. So all the crystal systems which are periodic in nature, okay, which represents translational periodicity, we will observe that they will fall into one of these 230 space groups. Okay. Space group really tell about, if we place motif around a point, that is what are the types of crystals which we can have. Okay. And if we do not consider the motif, okay, if we look at only the lattice points, then we have only 14 Bravais lattices are there, to which if we add all the symmetry elements and put motifs around it satisfying these symmetry elements, then the distinct crystal with distinct space group symmetry which we can have, the total number turns out to be 230. Okay. About glide we have already considered when we talked about two-dimensional point groups. Okay. What we have to consider is another type of an axis which is called as a screw axis. Okay. That is in a crystal like this. Okay. If we place a motif at some particular point, okay, to satisfy the symmetry, the motif should be kept at some points to satisfy this symmetry. There is another way in which it is, because the rotational symmetry is to satisfy. Other way in which it can happen is that along this direction, okay, one motif is kept there, another motif is possibly rotated and it comes here. Then after some rotation it comes back to it. From this motif to this motif which is there on this one with respect to lattice, they are in identical position. But to satisfy that symmetry, okay, it is not on a particular plane which is there, it is along an axis, the motif itself has been shifted. Okay. These sort of symmetry elements are exhibited by many crystals. This we call it as a screw axis. Okay. This is like a normal threaded screw when we rotate it one round by a pitch, it comes back to identical position, right? Exactly like this. But there are some conditions which this screw axis will have to satisfy, okay, so that the periodicity of the consistent with the translational periodicity of the lattice, okay. Suppose a crystal has got a two-fold rotation, okay. The possibility which it can have is that at one lattice point, okay, you look at it, these are all the two atom positions which are there, so that a two-fold rotation will be there. Another lattice point also there should be. At this point you have another type of a motif which is being kept, the same type of a motif which repeats itself, so that around this axis if we rotate it, two-fold rotation is always being maintained, correct? You see here, this one is there, this repeats itself, and the next lattice point it is there in an identical position. In between we have a point, this has been rotated by 180 degree but shifted by half the lattice parameter, okay. And again in this particular direction you notice that this has got a screw axis associated with in the lattice, okay. These sort of symmetries are exhibited by many molecular crystals, okay. This is essentially there is a convention which is being followed to represent it, okay, that we will come to, okay. At this point we should make a subtle distinction, because this is essentially, if you see here, it is rotated by 180 degree, then it will come like this here. What is the type of symmetry this one exhibits? Glide, okay. The difference essentially is that it is translated by half and then it is a reflection, okay. These two you can make out the subtle difference between these two symmetry elements, correct? So what is the condition essentially is being followed is that from one lattice point to another lattice point if we move, okay, through some pitch which you take it to be Z, that is if m times tau the pitch equals t is the lattice translation vector in that direction, either it could be one lattice translation vector or some number n, okay. That is what essentially is given as p, okay. So what does this m represents? M represents the rotational symmetry which it has, okay. Then this will be p by m into t. If p turns out to be 1, that is like in this specific case which is being shown here, it has a 6-fold symmetry, okay. It is rotated by 60 degree and then translated by 1/6. Then after a complete 360 degree rotation, at the next lattice point it comes back to identical position, correct? That is what essentially is happening. But there are cases where it may not come back to identical position after one rotation, maybe after 2 rotation it can. Then what will happen is that, suppose that happens from here to here, what will happen to a pitch? Pitch has to be doubled, correct? Then only such a sort of a translation can occur. That is what this expression also tells. After 2 translation vectors if it has to happen, then the p will be 2 and then divided by m, which is the number of rotations, which is, that is the rotational symmetry of that in that direction. Then we can find out what is going to be the value of tau. Is this clear? Okay, let us consider this with an example of a 4-fold symmetry. Okay. In this, if you look at it, along this axis it has got a 4-fold rotational symmetry, right? Here also is a 4-fold is there by a parameter t, this direction it is repeating itself, you assume that it is going on like this, stacked one on top of the other. So, it exhibits a fourfold symmetry, right, and the periodicity is T. You look at this here. From here, there is a motif which is being kept here. It has been rotated by 90 degree and shifted by 1/4 of the lattice parameter in that direction, that is translation vector in that direction. It reaches here. Again rotated by 1/4, it reaches at the half. Again rotated by 1/4, it comes here. The fourth one, it has come back to an identical position, correct? Yeah? No. From here 1, 2, 3, 4. One is here. Okay. So this has come back. So this essentially is a fourfold rotation. Plus, if you look at the pitch, is turning out to be T by 4. Correct? And the direction, if you see it here, is in a what way we have taken it with respect to this. It's in a rotation is an anti-clockwise, right? You see this one. The same way you start with here, but it's in a clockwise rotation, it comes, okay? So both are possible, but both of them are distinct, they are not the same, correct? Is it not? Because here, after this position, one here it comes, here in the opposite direction it comes. See, there are two different types, but one is clockwise rotation and another is an anti-clockwise rotation. You look at this one, what do you see? Here, the motif itself has got a twofold symmetry is associated with it. This motif is rotated by the pitch is, if this is the pitch, it is by not 1/4 but half, and pitch is half, angle is 90 degree. Now it comes like this. When I rotate it again, another rotation, if I look at it, now it comes back to this position. It looks like similar, but it is not, because you understand that. Suppose I can put a marker on this one. This marker would have come here and this marker comes here. So that's not. Again, if it does one more double the rotation, it comes back to a original position, correct? In this particular case, the translation is 2 times, okay? That is what essentially this expression, this P means, okay? So if you look at it, if you compare with respect to these two, okay, now you can see that they are not the same. This is a 2-1, the symbol which is used 2-1, that I will come to, and here the symbol which is used as 4-2, okay, because the rotation which is given is 90 degree, here the rotation is 180 degree. Okay. So what we can make out here is that if this P turns out to be 1 in this case, okay, 1, and it is a twofold rotation, so this is represented as 2-1, okay. Similarly, when we consider the fourfold, we have a 4-1, okay, another is 4-2, that is corresponding to this one, okay. Then the other one is written as 4-3. Why it is written as 4-3? Because if you look with respect to the way, the clockwise and anti-clockwise if we consider, but it is equivalent to the other way down. If you do it in the opposite direction, it will be 1/3 of it which you have to rotate it to bring it to an identical position. Okay. See here what happens is that from here in the opposite direction, if you rotate, how much you have to rotate it to bring it to this position? 1/4 if you rotate it, you will be bringing it to a position which is identical with it. With respect to this, if I rotate it in this direction, 1/4, this is equivalent to 1 minus in this opposite direction, okay, 1 minus 1/4, that is how it is being considered. So essentially this is equivalent to, if we take a pitch of 3/4 and then take it along, okay, then we will notice that this will turn out to be the same, identical to it. Okay. But why we are writing it in this way is that we are following one convention of taking the sense of rotation. Okay. Because here the way we considered is, in one case the sense of rotation is clockwise and another is anti-clockwise. If we take the sense of rotation in the same way, we will notice it that it's going to be, that pitch is going to be not 1/4, it is going to be 3/4. Okay. Now if we consider similarly 3, we can have 3/1, 3/2, okay. 4 we have considered, 6 also we will have 6/1, 6/2, 6/6 will turn out to be essentially the 6/1 itself, that repeats itself. Okay. So these are all the number of screw axes which we can have in the lattices. Okay. Is this clear? This is in addition to, that is it, some crystals can exhibit with screw axis which is there. In some crystals it can be just a simple 2-fold or 3-fold or 4-fold or 6-fold rotation also. Okay. So now we know, I think 1, 2, 3, 4, 5, 11 types of screw axes are possible. Okay. Then mirror if we consider, okay, not mirror, glide. Okay. Glide also essentially a mirror and a translation together, right? It is a combination of both of them. With respect to a crystal, it can so happen that only along 001 axis we have the glide, okay. Other axis there is no glide, or it can be there along B axis or along C axis, or it can be along the face diagonal, or it can be along the body diagonal. All these directions we can have glide axis, that is possible in the crystal. Okay. If that is the case, then what is going to be the translation vector? That is what is given in this table. Okay. And then this is called as axial glide, diagonal glide, diamond glide and all. And the symbols which are used to represent them in International Union of Crystallography is A, B and C, because along A axis it will be A, B axis B, C axis it will be C which will be used, and whenever the diagonal glide is there, N is used, diamond glide, D is the symbol which will be used. Okay. Like we assume that the crystal has 4M, M. Okay. In this direction where mirror is there, okay, this is along 110 direction. Okay. If there is a, instead of a mirror, there is a glide is there in this direction, then the symbol will turn out to be 4MD, and if it is primitive, okay, we will be writing P4MD. This is the way this space group is represented. Is this clear? When the glide is not there, then the space group will be P4M. This is the way it will be. So what are the symmetry operations which we have for a space lattice? Or we have 1, 2, 3, 4 mirror, okay, inversion, roto inversion, glide, screw. We can have a combination of all of these put together, okay. That gives totally 230 space groups exhibit. Is it clear? And in the International Union of Crystallography, if you look at it, these space groups, if it has to be represented, because we are talking now with respect to a lattice, correct? And representing three-dimensional lattice, okay, in 2 dimension if he has to represent, generally we draw a cube and do it, but the cube doesn't, but looking at the cube we cannot tell that whether it is cube or whether it is a tetragonal lattice or an orthorhombic lattice unless and until we mention what are the lattice parameters, correct? Otherwise it could be anything, any one of these it could be. Okay. So the other way in which we can represent it is generally like what in mechanical engineers and civil engineers do is the plan and elevation, correct? So you look at the crystal, okay, then try to represent it in 2 directions. You look at it. So this is a projection which is given now of the crystal looking along 001 direction. This is how it looks, correct, for a tetragonal lattice. And this is how the projection which it will be in 010 direction, correct. Once these 2 projections are given, the crystal is completely specified. The lattice is the unit cell of the lattice is completely specified, correct. Complete information is available. Then similarly, if it is a body centered, then there will be one more atom position is going to be there. How do we represent it? Okay. The way in which it can be done is that you show this position at the center, because the projection it will be seen this as the projected onto this plane, correct, and then just mention half. That half means that it is sitting at a position halfway up, okay. That is how it is represented. Okay. Similarly, if it is a face centered 1 cubic, then these positions we mention it as half position, and the others we know that they are in that same plane. So these are all the way in which we can represent it. In fact, when you see many of the journal papers, they are also, when they wanted to show the projection of unit cell, quite often this method is followed. We will just take a few examples of, so this is the way in which a unit cell can be represented, okay. Then after representing the unit cell in this way, we can put motif around different positions and also show the symmetry elements which are associated with the unit cell. That is how it is represented diagrammatically in the International Union of Crystallography. What I have taken is the one which has got the monoclinic structure, which has got only a 2-fold symmetry, 1 2-fold symmetry axis, okay. So as you remember, for monoclinic I mentioned that 2-fold symmetry is taken along the B axis, correct. Okay. So here in this projection the B axis is normal to the screen, okay. This is A and this is C, okay. Then these are all the other 2 directions are also being shown projection. When these directions are being shown, it is complete in itself, correct. Then in addition to it, if you see here a symbol which is being shown with an arrow with a, okay. If this arrow is shown, this exhibits that it is a rotation axis is there along this direction. This is what it means, okay. These are all the symbols which I think in the book afterwards you will be able to see what each of these symbols mean, okay. And in the perpendicular direction what we show, this symbol if we show, it means that it is a 2-fold rotation is here, a 2-fold rotation around this point here as well as here, okay. if we take it, these are all the additional symmetry points which are generated in the lattice. Okay. And around this lattice, if we put a motif around here, okay, in this what one should consider is that what is the symmetry axis which is there? Only a twofold rotation, correct? Only one axis of symmetry is there. Then where do we fix the origin of the unit cell? Arbitrarily you can choose it anywhere on the axis. Suppose we have a, that is what is the case for many symmetry elements, where if the symmetry elements do not intersect, okay, then we have to fix the origin arbitrarily, like 4 mm or 2 mm, all of them. The mirror also is on the plane of the symmetry axis, correct? The symmetry axis, that is the rotational symmetry axis, and the mirror plane, they are parallel to each other. Okay. So origin you can choose arbitrarily. If the symmetry elements intersect, the point of intersection is always taken as the origin. Okay. That is the convention which is always followed. So because of that, here what is being done is that, that's why the motif is being placed at some position with respect to a coordinate system which has been chosen, origin of the coordinate system plus. Okay. Then around this axis which is perpendicular to this plane of the paper, plane of the screen, if it, since it's a twofold rotation is there, so another one will come at 180-degree rotation, correct? A motif has to be there. So this is how the general position is represented. Okay. This diagram represents the symmetry elements which are associated with the unit cell. This diagram represents the position of a motif when it is placed at a general point. Okay. What is essentially important is that to construct a crystal is this type of information, which is the tabular form which is being given, okay, about the coordinates of the various positions of special points as well as general points. Okay. At this point, if we consider what is the symmetry which it has? Twofold rotation, correct? Is it not? So if we keep any atom at this point, okay, if you put at this point, only here, 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 by translation they will be generated, okay, the unit cell will be completed in itself, okay. But it can, and since the origin is never fixed, the atom need not be kept at the origin, it can be kept on this y axis, anywhere also it can be kept. That is essentially what it means, that 0, y, 0. That is 0 with respect to here, 0 with respect to here. On the y axis it is kept at some position arbitrarily at y. Okay. Or the other position where it can be kept is that 0 on the x axis, that is a here, then half in this direction, okay, and y on top. That is, this is also another symmetry element. If I keep an atom at this position, okay, and then another atom at this position will come by translational symmetry. By translational symmetry, another will come here, another will come here. Again you notice that the monoclinic structure is being constructed. Okay. Similarly, an atom could be kept at this position. Okay. That is what this shows. Or the third, it would be kept at this center. This is what, this is the coordinates of the atom position which is being shown where we have to keep the atom. And then there is only one position where we have to keep it, because the others are all generated by translation, because here the P represents essentially a primitive lattice. Okay, primitive lattice means that number of atoms per unit cell is 1. So that is why essentially we have to choose only one position. Then if we keep it at a general point, Okay. Since it is a two-fold symmetry, there should be minimum 2 atoms per unit cell should be there. That is what you can see, that when atoms have been put at general point, this position and this position, it is going to be there. So, within the unit cell you have 2 are there. That is what this number 2 represents, the multiplicity. Okay. There are some reasons, the way in which one can reason out and find out how these are derived. Okay. That part I am not going into it. Okay. That those who are interested can read the book and Introduction to Crystal Geometry by Burgess. Okay. There it is all explained very nicely. Okay. And then I had also mentioned that when you know the rotation symmetry axis, how to find out when one position is given, the coordinates of the other positions we can find out, correct. So, this is the one which is very important, this table. Okay. So, the possibilities is that either an atom could be kept at this position, atom or a molecule, okay, or at this position or at this position or at this position. Okay. Then by translational symmetry they will be generated at other points. But what is essentially important is that the same atom cannot be kept at this position as well as this position and as well as this position. That is not possible. That I will come to later to explain it. So, these are all the possible position, either here or here or here or here. It is or, not and. This is essentially. Okay. No, in this table, if you see it here, in the crystallography, International Union of Crystallography table, okay, each page corresponding to a particular space group, a number is given. Like here, this number is 4, which is given for this one. Okay. And then it is written monoclinic, and this one shows what is the point group symmetry corresponding to it. Okay. The difference between point group symmetry and space group symmetry is that in the space group symmetry, if we remove the rotation axis, the screw or the glide, okay, what will be left behind? If we remove glide, then it becomes a simple mirror. If we remove screw, it becomes a simple rotation. Okay. That is how the space groups are mentioned. So, here if you look at it, this is just a shows the point group symmetry. Okay. This is the Schoenfly symbol, okay, and this is the space group symbol which is followed now. The 2-1 corresponds to two-fold rotation. Okay. This is a short symbol, this is the correct symbol. This symbol what is then primitive. Okay. Along x axis there is one-fold rotation, along y axis there is a two-fold screw axis is there, then on the z axis there is an one-fold rotation, correct. Now you look at this, in this one the symbol which is used for representing screw is this symbol. Okay. This is for a two-fold two-fold screw axis. Okay. Is this clear? Okay. Then as I mentioned earlier, and another thing also is that the projection which is there taken along the other perpendicular directions of the unit cell. Here the arrow which depicts is one side only, the arrow is there. If an arrow is put like that, this represents just a rotation. If we put an arrow like this, it represents a screw axis. Okay. There are various symbols are used to represent that. In a separate table all the symbols are given, what all symbols which are used. Here what is going to happen is that if we keep one motif at a particular point, another motif comes at half position. Okay. That is from wherever it is being kept, half the distance if we translate it and do a 180-degree rotation, that motif will come. That is why wherever this is 0 plus, this is the O plus, the O half plus it is given. Okay. In this particular case, the choice, if you look at, though here also we have a twofold, all these are possible. Okay. The coordinates, if you consider it, that positions which are possibly x, y, z, and another is it is x bar y plus half z. There are some ways in which these are represented. Okay. This I have already mentioned to you with respect to glide, how exactly it is done. Okay. And this is the method in which it is represented, these various types of operations, which is called as a size operator. Okay. You do not have to know about it, but I wanted you to be aware that this is the methodology which is being followed. In this symbol, this represents nothing but the rotation operation. This represents the translation operation. Okay. No, mirror operation. Okay. And this is R is the translation. So, this is what essentially here you can see that 1 0 means that it is an identity operation. Okay. Here 1 t by n means that it is an one-fold, okay, rotation is one-fold, then it is only just a translation which is taking place. Okay. Suppose we have a mirror is there, okay, then it is the mirror, whatever is the axis which you have to put it, the coordinates of this R is the position vector of the motif, then plus the translation which is being given. So, that is what it happens, that x, y, z, if there is a point is there, okay, that becomes, if the glide is along y axis, it is shifted by y plus half, correct, along the y axis, the next position. And when it reaches that position, when you take the mirror with respect to, when the mirror is on the y axis, the glide is along the y axis, it will be that x will become minus x. That is how these symbols I had explained already, okay, how it comes. Another case which we will consider is primitive lattice which has got 4 mm symmetry, point group symmetry. Okay. This is the way it is represented, it is a tetragonal, point group symmetry is 4 mm. Okay. This is the Schoenfly symbol. Okay. So, what are symmetry elements which are there associated with it? At the corner points of the lattice we have 4-fold, at the middle we have a 4-fold, correct. Then at the edge and middle, okay, if you look at it, we have a 2-fold symmetry is there. Then 2 types of mirrors which are seen, correct. So, all of these, okay, and you should understand that here also, since it is a 4 mm symmetry, the origin is, we can arbitrarily fix it, because 4-fold rotation axis, the mirror are parallel to each other, so they never intersect. Okay. That is the reason why when we give the position where a motif or an atom can be kept, here it is given 0 0, z is given, because this is the z is the axis around which the 4-fold rotation axis is there. Okay. So, suppose we fix the origin corresponding to the atom position, then this will turn out to be 0 0, correct. So, this corresponds to an atom being kept at this particular position, the origin, okay. Then it will be 0 0 z or 0 0 0, it can be both possible. Okay. Then by translational symmetry, other 4 positions the atoms will come, the unit cell gets completed, correct. Okay. Then at the center of this unit cell also, this also another special point where symmetry elements are meeting. So, this also has got a 4 mm symmetry associated with it. If you look at it, that is mirrors pass through, a fourfold rotation is also there. Okay, that is the side symmetry. Okay, and this position in the Wyckoff position, this is given as A, this is called as B, and the number of position atoms which have to be kept, or the motif which has to be kept at this point is only 1. Okay. Then by symmetry operation, the others will be that by translational symmetry operation, the other lattice points will be generated. If we keep one here, okay, which corresponds to 2 mm symmetry, then 2 positions are possible here as well as here. Okay. Then by translational symmetry, these 2 will also be generated. Okay. So like that, for all the possible special positions, okay, what are the places at which the motif should be kept, that information is being given here. Okay. And if you put at a general point like what is being shown in this diagram in the International Union of Crystallography table, and here that if x, y, z is will be a general point, right? Because whenever anything is related by symmetry, okay, if you write a coordinate, if I write xx, z means that x as well as y, they have the same distance, right? Whenever this sort of notation comes, that means that this point is a point which is related by some symmetry operation. Okay, that is a special point. That is what you can see here. Here when that m is there, you see that xx is it is written, right? Like here you see that x0 is z, okay. Similar thing you will notice it. And here when it comes, it is x, y, z which is being used. Okay. All the 3 are distinctly different. That means that that represents a general point. Okay. And here what I have shown is what this ABC means, okay, corresponding to this one. These are all the Wyckoff positions which are given. That side symmetry I have already explained what it means. Okay. The same information presented it in a different way. Okay. That is, we can have a position where at the center we can put an atom position, or one we can put it at this particular position, or it can be kept at these positions, okay, or at these positions we can put that motifs, or we can put at these positions, or these positions if we put it motif. All of them exhibit, okay, 4 mm symmetry is exhibited. Okay. But what is essentially important is that suppose I put a one type of an atom here, okay, the same type of an atom at this point, then what is going to happen is that this essentially is a P4 mm, correct? And if I put one here and an identical atom here, then one has come at the middle, then the symmetry changes to I4 mm. So that is not the same. Okay. So same atom cannot be placed at 2 types of Wyckoff positions. But these are all the, as I mentioned earlier, whatever we are talking about is a geometrical crystallography. In geometrical crystallography, we are looking at what are the possible positions in which motifs can be kept, okay, which satisfies the symmetry element. That is what we are looking at it. Because now you can see here also the same thing which I am shown. Like if I put an atom here, by translational symmetry, this will be generated, this point, all these points are generated. This is what is generated as the Wyckoff table mentioned as a 4A. Okay. This is one way in which it can be filled. If the same atom I wanted to keep it in this position, then this is the way it will appear in the unit cell. Or if it is at 2C, which is the 2 mm symmetry is there, these are all the positions with respect to a unit cell which is chosen. These are all the positions at which the atom should be placed. Okay. With respect to a unit cell which is chosen, if it is for one type of a mirror, atoms will be kept at this position. For another type of a mirror, the atoms will be kept at this position. For another type, atoms will be kept at this position with respect to a unit cell. So, any one of these type we can use, but are each one of them, when we keep an atom at this particular position, each of them independently satisfy the 4mm symmetry. You understand that? Whether I keep an atom here and generate a crystal, or whether I keep an atom here and generate a crystal with respect to a unit cell, or whether I keep an atom at this position and generate the crystal, or in this or this one, all of them satisfy 4mm symmetry. Is it clear? Okay. What I will do it is, I will stop here now. Okay. We will continue in the next class.